The input layer is where data first enters the network. It serves as the bridge between raw data and the complex layers of neurons that follow. But what exactly goes into designing this layer? The input layer is where data first enters the neural network. It acts as the interface between raw data and the deeper layers of neurons. Designing this layer involves choosing the right format and structure to ensure the network can effectively learn from the data. The input layer is where data first enters the neural network. It acts as the interface between raw data and the deeper layers of neurons. Designing this layer involves choosing the right format and structure to ensure the network can effectively learn from the data. Next up is how your data is represented. Each node in the input layer corresponds to a feature. For numerical data, this is straightforward. The feature value goes directly into the node. For categorical data, we often need to transform it into a numerical format, like one-hot encoding, before feeding it into the input layer. One-hot encoding turns each category into a unique binary vector, where only one element is set to 1 and all others are set to 0. This allows the network to interpret categorical features as distinct and separate, avoiding any unintended hierarchical relationships between the categories that could occur if they were assigned arbitrary numerical values. Normalization is also a key step. Input values are often scaled to a range like 0 to 1 or -1 to 1, which helps the network learn more efficiently. This scaling prevents large input values from dominating the learning process and ensures numerical stability during training. By having inputs on a similar scale, the network can converge faster and avoid issues like exploding or vanishing gradients. Additionally, normalization helps gradient descent methods operate more effectively, as it keeps the learning rate consistent across different features, ensuring smoother and more reliable optimization. Different types of data require different handling. Numerical data feeds directly into the input layer, but categorical data needs to be encoded. For sequential data, like text or time series, we usually process it through embedding layers or recurrent structures before it enters the network. For example, in a recurrent neural network, the input layer might take a sequence of words from a sentence, processing each word step by step. The input layer is fully connected to the first hidden layer. Each node in the input layer is connected to every node in the next layer. The weights of these connections are learned during the training process, determining how strongly each input feature influences the neurons in the hidden layer. Before data even reaches the input layer, it often undergoes preprocessing. This might include scaling, normalization, or even more complex tasks like feature selection or extraction. The goal is to present the data in a form that the network can effectively process. The design of the input layer can vary depending on the architecture of the network. In convolutional neural networks, the input retains the spatial structure of images, whereas in recurrent networks, the input is typically sequences. Transformers, on the other hand, often embed input data into vectors before processing. In summary, the input layer is your network's first impression of the data. A well-designed input layer ensures that the network receives data in the most effective way possible, setting the stage for everything that follows.